Hi guys, I'm Brooke Hendrickson, and today I'm going to teach you all a little bit more about the photoelectric effect. And the photoelectric effect is super interesting, and today we're going to talk a little bit about the etymology of the word photoelectric, about the history that led to the discovery of the photoelectric effect. We're also going to talk about Einstein's experiment that he used to discover the photoelectric effect, along with the difference between quantized and continuous measurement, as well as photons and what they are, the 5 token characteristics of the photoelectric effect, and some practical applications of the photoelectric effect that we see in our everyday lives. Okay, so to get started, we're going to talk a little bit about the etymology like I mentioned. So I really like the etymology of this word because it describes exactly what it is. So the first part is derived from the Greek word phos, which means light, and the second part being electric, which obviously means electricity. So we're going to look at how light can produce electricity based on the electrons that are ejected when we shine light at different types of metals. So to talk a little bit about the history of the discovery of the photoelectric effect, it was discovered by Albert Einstein in 1905, and he later went on to win the Nobel Prize for his discovery of the photoelectric effect. And to me, this part was really interesting because we always think of Einstein associated with his theory of general relativity and special relativity, but he actually didn't win the Nobel Prize for that. It was too complicated for people at the time, they didn't understand it. But he did win a Nobel Prize for his discovery of the photoelectric effect. And this was really important because at the time of the discovery of the photoelectric effect, there was a lot of debate over whether light behaved as a wave or whether it behaved as a stream of particles. And that was a big debate among a lot of scientists, and it was a big area of confusion. So when Einstein resolved this using the photoelectric effect, it led to the development of quantum mechanics, as we know it today, which is super important to modern physics. The experiment that Einstein used to discover the photoelectric effect is somewhat simple, actually. So what he did is he put a light source above a sheet of metal, and in the metal there's a bunch of electrons on the surface of the metal. So when he shone the light at the metal, what he found was that the electrons were excited by the light energy and ejected from the sheet of metal. And we're going to talk a little bit later about some of the characteristics of that experiment that led him to believe that energy is quantized. But before we do that, we're going to talk about the difference between quantized and continuous measurements. So we're going to use an analogy of stairs and a hill. So quantized measurements is like taking stairs to get up a hill, whereas continuous measurement is like just walking up the hill alongside the stairs. And the reason I say that is because on stairs you can only go up by discrete quantities every time. So you can only be at certain set elevations as you move up the hill, for example. Whereas on a continuous slope, you can be theoretically at every conceivable elevation on the slope. So quantized measurement basically just means that energy comes in packets or little particles. So you can't have like 1.25 or something like that. It has to be like 1, 2, 3, 4, 5. Whereas continuous, you could have 1.1, 1.2, 1.3, 1.4, 1.5, etc. Okay, so these little energy packets that Einstein discovered are known as photons. And a photon, like I mentioned, is basically just a little packet of light, a little packet of energy. And that little packet of energy is a little wave packet. So it combined the theory of particle waves or particle light and wave light. So we can see here, I just did like a theoretical representation of a particle with a little wave in it to kind of describe that effect of him combining the two theories. And the energy encapsulated in a single photon is described by the formula E equals hf, where h equals Planck's constant and f is equal to the frequency of the wave inside of the photon. So to just kind of illustrate that, I did this drawing here where this would be a lower energy photon and this would be a higher energy photon because this one has a higher frequency than this one. Okay, so now we're going to move on to the 5 token characteristics of the photoelectric effect. The first characteristic is that each individual electron interacts with an individual photon. And because of that 1-to-1 ratio, what we end up seeing is that in order for an electron to be ejected from the sheet of metal, we have to have a photon that reaches the threshold frequency of the metal. So if it doesn't have the threshold frequency, electrons won't be ejected regardless of the intensity of the light. The second one is that electrons are ejected immediately when when the photon reaches threshold. So once the photon is at threshold and it hits the sheet of metal, the electrons will automatically be ejected from the sheet. And this proves that light has particle characteristics, because if it were to be a wave, it would take time for the wave motion to excite the particles enough for them to actually be ejected from the metal. The third one is that the rate at which electrons are ejected is proportional to the intensity of the light. And this makes sense going back to our 1-to-1 ratio, because intensity basically just describes how many photons are there per unit area. And if there's more photons per unit area, we're going to have more electrons interacting with more photons and being ejected from the sheet of metal. The fourth one is that ejected electrons have kinetic energy when they're ejected, and that their kinetic energy is dependent on the frequency of the photon that hits them. So basically what that's saying is that it's independent of the intensity of the light and dependent on the frequency, and that the energy from the photon is transferred into the electron so that the electron can fly off of the sheet of metal with some sort of kinetic energy. So the fifth characteristic that we're going to talk about, and the last characteristic, plays into the fourth characteristic when we were talking about how electrons are ejected with a certain kinetic energy depending on the frequency of the photon that hits them. So basically the fifth principle describes how the kinetic energy depends both on the energy of the photon that hits the sheet of metal and the binding energy of the metal. So what we mean by binding energy is the amount of energy it takes to excite an electron to the point that it will leave the metal, so it'll fly off of the metal. And what we see here with this graph is that the kinetic energy depends principally on the frequency. So the F0 here describes the threshold frequency, and as we cross the threshold frequency, we can see a proportional increase in the kinetic energy as we increase frequency. And some practical applications of the photoelectric effect. So I think the photoelectric effect is really cool because it led to a lot of discoveries of theoretical things like general relativity, special relativity, and other parts of quantum mechanics. But another reason that it's really cool is because we can see it in our everyday lives. And one way that I see the photoelectric effect in my everyday life is through solar panels. So basically what's happening with a solar panel is what we were talking about with the experiment that Einstein ran. It's at this time, instead of a light bulb being the source, we have the sun being a source of photons and energy. So as the sun emits these photons, the photons strike the sheets of metal that we have and eject electrons, and then these electrons are then channeled into an electrical current, which can be used to power our homes, buildings, schools, and everything else, up to solar paneled satellites and other important things. And it will be really important in the future for sustainable energy. Thanks for listening to my presentation about the photoelectric effect, and I hope that you all learned something from it.